Hello everyone, welcome to 12.2, and today we're going to be learning about geometric sequence and day 1. So in this lesson you guys will be working with a sequence that has a new pattern. So we've been working with arithmetic sequence for the last couple of days, and that is when the numbers keep adding or subtracting the same number to get to the next term in the sequence. So geometric sequence is going to take a little bit of a different direction. Instead of adding and subtracting, the numbers are going to be multiplying or dividing, and basically just multiplying to get to the next term. So you will be working with geometric sequence today. And let's take a look at how that is in an example. As a tree grows, a limb branch off of the trunk, and then smaller limb branches off these limbs, and each branch splits off into smaller and smaller, the same way throughout the entire tree. So here's an illustration of it. In stage 0, there is no new leaves, right? No new branches. But in stage 1, the 2 new leaves, 2 new branches grow off, and then in stage 2, 2 more new ones. So you can take a look at the number of branches right here. It goes two new ones, and in this stage it goes 4, and here is 8. So if we can continue, start a table to illustrate that, that goes right here, and notice that the number of new branches is always doubling, right? You are multiplying by 2 to get to the next stage. So if you follow this, the next number of branches that will grow from these will be 16, because you will get 8 of these, each will get double, correct? So right here, you will have double, So the pattern will just keep going. So it'll be 32 and then 64. And if we just continue to write this as a power of base 2, this will be 2 to the 4th, 2 to the 5th, and 2 to the 6th power. If we want to summarize this in an equation or as a rule, you will notice that the n for the number of branches at stage S, like at the end right here, at any stage S, we can summarize that as in 2 raised to the S power, because whatever the stage is, that would end up being the power. So if S is the stage, then it will be the power. So n of S is going to give me 2 to the S. That will be the rule to summarize the number of new branches growing. Let's take a look at what that looks like in a graph. So if we were to graph the first 5 values, which are these right here, from 0 to 4, it will be based on what we already have. 0 is already there. At 1, we're going to have 2. So here's 2. And then at 2 is going to be 4. At 3 is going to be 8. And then at 4 is going to be 16. So if you follow this, it does not form, you notice that it does not form a linear graph anymore. So in the arithmetic, we notice that we would always have a linear function that is graph, right? But in here, you actually notice that it's kind of like a curve. So that's the difference between arithmetic and geometric. So in a geometric relation, you are going to have a curved shape for your graph. And so to generalize the graph, as the number of stage increase, the number of branches also increase. So it goes up as you move on. So it goes in an upper motion right here. So as S increases, n of S also increases. So that would be the answer for that question. Let's take a look at the next thing here, part E. Now fill in the table for the branch of the length, right? So the length of the branch. So we're going to go back to the illustration here. If you notice, when we are talking about the length, what do you notice about the length of the new branches? Is it the same size as the original one? Notice that it's smaller. It is actually half the size of the original. And every new one shows up is only half of the size of the previous one. So that would be the pattern here. So in table E, it shows right here, in the table here, shows that the length is actually being multiplied by half. So to get to the next one, it will be 1/4 times 1/2, which is 1/8, and then 1/16, and so on and so forth. So if we were to rewrite this as a power, right here, notice that this is 2 to the 1, 2 to the second, 2 to the third. So whatever the stage is, that would be the power. So at the nth stage, it would be 1/2 to the n. And we can write that as L for the length of S is equal to 1/2 to the S. Just change that n to S, and that will be the length formula. To graph this one, it's a little different than the previous one. So we start with at 0 stage, it is the length, full length of 1, full size. And then the new one is going to be only half the size. So at stage 1, it's half. And then stage 2, it will be 1/4. Stage 3, 1/8, and so on, so forth. So notice that this one is going in a decreasing motion. So the curve can go down. This type of a graph will be called a decay. So we're going to learn about that later on. Whereas the one from above, this is a growth. So this is a growth motion. And then, so in geometric, there's two types. There's a growth, and then there's a decay, as in illustrated in this one right here. So as the stage increase, notice that the graph is going down. So that's decreasing. So the length decreases. It eventually approaches 0, but it will not get there. So that is the pattern for this example right here. Hopefully you understand a little bit more about geometric sequence. So we're going to take a look at the definition of geometric sequence. It is a sequence with a ratio of the consecutive terms that are the same. So if we, again, if you multiply the same number every single time, it will give you the next term. So that number in arithmetic sequence, it was called D for common difference. And here it is called R for common ratio. So difference and ratio. Okay, so here we have a common ratio. So here are the two formulas again for explicit and recursive. And the formula is f of n for the term that begins with 0, a times r to the n power. And for the one that begins with the first term 1, it'll be a times n r to the n minus 1. And then recursive rules are the same as the previous one. You take the ratio times the previous term. So it's always ratio times the previous term. So let's take a look at an example and how to use those formulas and apply to some examples. So in example 1, it says to determine if each of the following is a geometric sequence. If so, determine the common ratio. So again, we're going to have to try to develop or find a pattern that will go from one number to the next one. So from here 2 to 4, we just multiply by 2. That's easy. From 4 to 8, we are multiplying by 2. Hey, that's consistent. 8 times 2 is 16. And does that work also for this one? So yes, this is actually a geometric sequence. And what is the common ratio? So we can just take any number divided by the previous one. So the ratio is going to be 4/2, which is 2 in this case. And let's take a look at number 2. From 1 to 5, I times 5. Remember, you're always going to try to multiply. Here, 5 times 9, I don't know what number to multiply. And it looks like that is consistent throughout the whole list. I don't have a pattern. So I'm going to conclude that no, there is no such thing as this is not a geometric sequence. Another way you can look at it is if you can divide the second number, R1 is going to be 5/1, which is 5. R2 for the next one is going to be 9/5, which is not equal to 5. So they are not consistent. So you can also say that because they're not consistent, this is not a geometric sequence. Let's take a look at the next one here. For the first two terms, from 1 to -1, you can multiply by -1. And -1 times -1 will give me 1, and looks like I am always multiplying by -1 to get to the next term. So this is a yes, and the common ratio is -1 over 1, which is -1. So you're always multiplying by -1. It is also demonstrated right here, the common ratio. And the last one here on this list is we can take a look at another way. You can just, instead of trying to guess what it is, you can just go ahead and do the math. 2/3 divided by 2, that's multiplying by 1/2, right? That's equal to 1/3. And then if we take the next one, 2/9 divided by 2/3, that's multiplying by 3/2. You can reduce that to 1/3. And it looks like if you follow the pattern, multiplying by 1/3, that will give you to the next term. So it looks like it's consistent. So this is a yes, and the common ratio is going to be 1/3 because we just did the math like right here to show it. Okay, so that is the end of that problem. And let's go ahead and have you guys try these two on your own. Go ahead and pause the video and then try this before you check your answers. So let's take a look and see if you guys got it right. So for the common ratio, the first one, R1, is going to be 18/3, and that is 6. And let's check to see if that is consistent for the next one. If I multiply this by 6, will I get to the next number? And looks like 108 divided by 18 is also 6. So it is consistent, and it also is 108 times 6 is 648. So this is a yes, and a common ratio, we already know, equals 6. And that's the end of that problem. Next one, we can do the math again. 1 divided by 0.5, that's actually going to give me 2. But if you take 4 divided by 1, that's 4. So they are not equal. So therefore, I can already right away say, no, this is not a list of geometric sequence. So that's the end of that problem. Example 2. Use the explicit rule given to write the first 3 terms of each sequence. So we're going to just follow the formula and make a list. So we're going to start with f of 1, which is 3 times 5 to the 1 minus 1, and that is 0. So anything to the 0 power is 1. 1 times 3 is 3. So 3 times 1 is 3, and I'm going to start the list. It's 3. F of 2, if you actually want to go about it in a smarter way, like, to get some shortcuts, if you understand this pattern, and from here, you can identify the common difference is actually 3. Right? Because the formula says that it is actually initial is 3. The common ratio is actually inside the parentheses. This is R. This is A times R to the minus 1, right? So R is 5. So you're actually going to multiply by 5 to get to the next number. So if you actually think about that, if I times 5, the next number should be 15. I'm just going to double check to make sure that that is correct. And that's 2 minus 1. That's 3 times 5. Hey, that is 15. And that means I can follow this rule for the next one. So times 5 will give me 75. So f of 3 is going to be 75. And there is my list of the first 3 terms. So if I use the same pattern, I can say that R is equal to 5 again here. So I can just actually go f of 1 is negative 2.5 times 1 minus 1, 0. So that's going to be just 2.5. So if I start with negative 2.5 here, and I know the common ratio is 5, I can multiply by 5. So f of 2 is going to be negative 2.5 times 5, which is negative 62.5. And then f of 3 is going to be negative 62.5 times 5, which will give, I think I skipped the problem here. It should be negative 12.5, and then here is negative 62.5. So that looks better. 12.5 negative, and then negative 62.5. So that's the list of the first 3 terms. Of course, you can also do the math like we did here to get those numbers as well. And and looks like that's the end of day 1. So you can go ahead and get started with your assignment, and have a good day. See you tomorrow.